So in the third mini lecture of the takeoff performance, we will learn how to estimate the ground run distance. So we know the takeoff distance is addition of the ground run distance and the airborne distance to screen height. And since you can see the ground run distance is highlighted in red, we are looking at the ground run distance. And now let's first consider small time frame delta t, and we can have the small distance moved by the aircraft equals v, that's the velocity of the speed of the aircraft, times delta t. And then we do some manipulation. We on the right hand side of the equation, we times delta v and divide it by delta v. Let's see what happens. Okay, so we move around different terms. So on the left hand side, we have delta v over delta t equals speed times delta v times divided by delta s. Okay, so we can rewrite it in the differential form, dv over dt. We know that's acceleration equals v times dv divided by ds. Okay, so we've analyzed forces acting on the aircraft during ground run, and these are the forces described before. Okay, so we also have this following the second law. We have on the left hand side is m times acceleration equals the horizontal force. So thrust minus drag, aerodynamic drag, divided by the friction drag of the aircraft. Okay, so we name the above equation as 1, the current equation as 2. Okay, so we have equation 1 and 2, and we combine them together, so we can have something here. So v times ds over dv over ds equals thrust minus aerodynamic drag minus the friction drag divided by the mass of the aircraft. Okay, so let's do something further. We can rewrite it as this. Especially on the right hand side, we can rewrite m as w over g. W is the weight of the aircraft because on the numerator we have w. Okay. So in a previous slide, we have this equation. And now let's assume thrust is a constant and L can be written as lift, that's actually lift half rho v squared times S times CL, and D is half rho v squared times S times CD. Okay, so now we plug in all these things, lift and drag, so we can expand the right hand side, and we just reorganize it and put CL and CD together, and we just write down ds explicitly because eventually we want to get the ground run distance. Ds is in incremental ground run distance, and then right hand side is like this. Okay, so the distance required from rest to speed v, then we we can do the integration. So that's a distance s. We integrate ds from 0 to s, and on the right hand side we have the velocity integration from 0, from rest, from stationary, because for ground run aircraft originally is stationary, and then we have the velocity, lift off velocity. Okay, so if we do the integration and reorganize it, basically what we did is divide by W and above and below, so you can have this. Okay, so you can see the red and the green, and we can write the red components as C1 and the green component as C2, so we can further simplify the integration. So that looks familiar to us and also looks simpler. Let's see how can we work on this further. Okay, just now we had this, and it's a simplified form. We replace something by C1 and C2. And then we first integrate against the v, so then now we are integrating against the v square. So you can see on the denominator we have v square, and then differential part we have v square. Okay, so from calculus we have this kind of solution. And now we can, and it's very similar to the integration of S. So we can just compare these two expressions. Then we can have the ground run distance as this. So you can have a better look. I can't read through it. And so basically it's this. Now what we need to do is replace C1 and C2 by these two terms. Okay, eventually the ground run distance can be calculated as this. So remember, this equation applies for the aircraft ground run from stationary to the liftoff speed, uh, VLOF usually. Okay, so it looks very complicated, but if we go through the procedure, it's not that difficult. Okay, so we derive the ground run distance from stationary to liftoff speed. Now let's have a look at example and try this example by applying this equation, ground run distance equation. So now we consider commercial twin turbofan transport aircraft with the following specifications. You can see here, and then we're asked to estimate the distance required for the aircraft to reach the liftoff speed SLOF. Okay, so let's first go through the parameters we are offered. First of all, we have the liftoff speed. It's 145 knots, or we can convert into meter per second. And then we have the max takeoff gross weight. That's the weight of the aircraft. Basically, we call it weight, but it's mass actually. It's 175.7 tons. And then we have the wing platform area. That's an S, 86.5 meters square, and a wing lift coefficient with takeoff flaps. So that's for lift takeoff configuration. So CL is 1.0, and then we have wingspan is 47.57 meter, and also we have the Osborne efficiency number E equals 0.7. This E number, efficiency number, is used to consider the induced drag due to lift generation. And then also we have ground effect factor, that's 0.4, because during ground run, there is a ground effect which is beneficial for lift generation and also for drag generation. Okay, then we have 3 CD. The first CD is for fuselage, wing, tailplane, and nacelles, and it's denoted as CDAC. So that's basically the aerodynamic drag for the aircraft configuration. We have also CD for undercarriage, and that's a number which is slightly larger than CDAC. And also we have CD for flaps at takeoff setting. So CDF, and it's quite small compared to the other two. So we have 3 CDs, and that contributes to the total CD also. And also we have the coefficient of rolling friction, and that's used to calculate the friction drag, because undercarriage is still applied. And also we have the static engine thrust, and in the bracket says it's only for one engine, but in this aircraft we have 2 turbofans, which means eventually we need to times it by 2. So that's single engine thrust, and it's constant. We assume it's a constant, right? And then we can apply these numbers into the S equation. Okay, so now we have all the numbers and see how we can walk through it. First of all, we have the weight, M times G, and that's the total weight of the aircraft, takeoff weight. And then we have the parasitic drag, as I said, that's a contribution or addition by the aerodynamic drag, undercarriage drag, and flap drags. So that's a total, or the parasitic drag coefficient. And now we want to get the induced drag. So in order to consider the induced drag, we first need to have the aspect ratio, b squared divided by the s. This s is the wing area, so that's 7.9. That's the aspect ratio of this wing. And then we have the induced drag, including the ground effect. So CDI, so kg is the ground effect coefficient, and it's 0.4, which means the drag is smaller during ground run. And on the other hand, we have CL squared divided by pi. E is a Oswald efficiency number we've seen just now. AR is an aspect ratio. So CDI, induced drag coefficient, is 0.023, which is about half the magnitude of CD parasitic. Okay, then the total drag coefficient is addition of CDP and CDI. And that means it has two components. One is a parasitic drag, and the other is induced drag. Okay, so then we just plug in CL and CD and difference thrust, weight, etc. And then eventually we know the lift of distance from stationary to the lift of speed is 1,115 meter. So that's the total distance required to take for taking off or for ground run. Okay, so now we need to consider the thrust effect on the lift-off distance because we assume the thrust is a constant. In this case, in the example, the thrust is 55,600 pounds. It's a constant, but in reality, the thrust changes with velocity. A more realistic model of the engine thrust has a quadratic variation of thrust with speed. So it's for that typical aircraft, it looks like this. So you can see on the right-hand side, the thrust changes with speed, and the unit for speed V here is meter per second. For the thrust is Newton. Okay, and if we have a graph, this engine, turbofan engine, and the thrust in pound changes with speed in knots is showing here. So if the velocity is zero, speed is zero, so it has maximum thrust. The thrust then decreases with increasing speed. And for the takeoff, liftoff speed, 145 knots, that corresponds to a thrust of 46,437 pound force. So that's smaller than the stationary one when it's as stationary. Okay, so which means the distance should be affected by the changing thrust. Okay, now let's see an improved solution by considering the thrust variation for that typical example. Okay, so what we can do is to calculate SLF liftoff distance using thrust determined at liftoff speed. So basically, if we know the liftoff speed is 74.594 meter per second, then that gives us a thrust of 206 kilonewton. Okay, so if we use this final thrust as an estimation, and then we do the average of this result and the result before. Okay, so use the new thrust and applying to the equation, we can get the ground run distance is 1,370 meter. Okay, so with a thrust, larger thrust at velocity being zero, we have liftoff distance 1115. And if we use smaller thrust, which is corresponding to the liftoff speed, we have the liftoff distance larger because it makes sense because if you have smaller thrust, so it takes longer distance to accelerate to that speed, right? So we know with two types of thrusts, and we get different ground run distances. Then we do the average. So this is more realistic estimation or more accurate estimation. So that gives 1,243 meters in total for the ground run distance. Okay, so for now, we can make a conclusion. The thrust output from engines affects the takeoff distance. Okay, so you can see the difference is about 100 meters. Okay, the example here is a simplified case. Yes, so because we consider thrust is constant, in reality, more parameters should be considered. For example, the runway altitude, because it affects the density, and ambient air temperature, runway slope, and or head and tail wind during ground run. So all these parameters contribute to the ground run distance estimation.